Hi, my name is Inês Oliveira.
Hi, my name is João Coelho.
Hello everyone, I am João Faria.
Hello, my dear scientific colleagues. My name is Luís Macedo.
We are from Portugal and we are not someone who settles just by living on this beautiful planet Earth and not knowing its deepest secrets and how its systems work. We want to know more. We want to make science. We want to be science.
So we went to Lousal, a small mining village in Portugal, on a 4-day scientific trip organized by our Ieso mentors, where we made several experiments and field observations so we could understand its geological context and the interaction of the mine and its infrastructures with the environment and all the Earth systems, such as atmosphere, biosphere, geosphere, and hydrosphere. With our investigation, not only do we intend to show you the importance of the exploitation of mineral resources, but also to explain how to exploit them safely and correctly. We will demonstrate to you, by using the old mine of Lousal as an analogy, the importance of mining in society, economy, and the environment. Our presentation will be divided in two main themes, which are mines as sources of mineral resources for the sustainable development of society and the impact of mining activity and respective solutions, environment and society. Theme 1.
But first, let's understand some concepts, starting by what mineral resources are. A mineral resource is a concentration or occurrence of solid material of economic interest in the Earth's crust, in such form, grade, or quality and quantity that there are reasonable prospects for eventual economic extraction. Mineral resources can be metallic or non-metallic. Let's look at this cartoon of a typical Portuguese college bedroom and watch how many mineral resources are used for the objects we use daily. Just so you can see, mineral resources are so important that all 6 basic needs that every human has directly involve them.
Food, for example, has chemical elements without which we cannot survive, just like everything we touch does.
So it's unavoidable to conclude that mineral resources are essential to society. They are in almost everything we touch or see. And this leads us to another question. Where do we get them? Non-metallic mineral resources are obtained directly from Earth's crust and through non-metallic minerals, such as quartz or diamond. Metallic mineral resources are obtained through the exploitation of metallic minerals. Every metal is extracted from minerals that are then considered ores. Ores are exploited in mines, thus the necessity of their existence in society. Without them, we wouldn't survive.
One of our practical exercises was to determine the mineralogy and chemical composition of 10 ores that were provided to our team by our Ieso mentors. To obtain the chemical analysis, we applied an analytical technique called X-ray fluorescence spectrometry, XRF, using an XRF portable analyzer. And the results obtained are presented in this table.
In this table, we can see the mineralogy of the ores we analyzed and their chemical composition.
Most of these ores are from the Iberian Pyrite Belt, IPB, which is a very important metallogenic district for the exploitation of copper, zinc, and lead present in sulfides, and the tin present in cassiterite, a tin oxide. As you can see, it is located in the south of Portugal and the southwest of Spain.
In fact, the IPB has some of the biggest deposits of sulfides in the world. This is the reason why there are so many mines in the IPB. In our 4-day research, we visited the mine of Lousal, an old mine where pyrite was exploited for sulfuric acid, to produce fertilizers. The Lousal deposit was found by a local farmer in 1882, but its exploitation only became intensive in the 1930s. Pyrite was one of the biggest sources of sulfur at the time.
However, the mine stopped being profitable in the late 80s. Consumers of sulfuric acid stopped using sulfur from pyrite and start using the sulfur that resulted from the recovery of acid gases of oil, which was a much cheaper process. Therefore, the mine of Lousal closed in 1988.
Theme 2. Looking more deeply into the consequences of mining activity, in a very simplified way they can be grouped into 2 distinct categories, the socioeconomic and the environmental ones. Within each one there are benefits as well as concerns. Starting by the former, we have more raw materials available, new employment posts, greater wealth, and residential and tourist attractions as benefits. On the other hand, there are sundry concerns as human and child exploitation, workers' health problems, and socioeconomic overdependence on mining, especially in the less developed countries. Moving to the latter, the positive impact is essentially the expansion of the renewable green industry, while the negative ones are the overexploitation and resource depletion, so as the soil and phreatic acidification and contamination.
Looking at its impacts, we understand that the mining activity is a paradoxical anthropic engine of evolution and pollution. Therefore, this sector must be carried out sustainably in order to ensure only its positive side. To achieve this, all countries and its enterprises should assume their responsibilities and value all land equally instead of acting in a selfish way. Not in my backyard is a movement and a fake way of solving problems by relocating them too far away, which the Western developed countries have been adopting.
In the vicinity of the ancient mine of Losal, there are 3 artificial acid lagoons, which resulted from a process of heap leaching. In order to fill the abandoned mining tunnels, in the past, the workers created excavations on the surface to extract the necessary materials. These open pits became so deep that they reached the water table and turned into the lakes we currently observe. Along the lakes passes a natural water stream, which in the past, when coming into contact with them, used to become contaminated, causing the degradation of the natural habitats downstream.
In the Losal mine area, we were able to distinguish 3 main hydrological flows, which we named according to their characteristics. In this way, we called natural flow the natural water course represented by the Corona stream, we called mining flow a water course that comes directly from the heap zone, and we called bioremediation flow a wetland system for phytoremediation of acid waters that will be described ahead. After observing the area, we designed a sampling plan to collect and analyze water samples to understand if and how they were impacted by acid mine drainage processes. First, we collected water samples from 2 sides of the natural flow upstream the mine spoil area, natural flow site 1 and natural flow site 2. Then, we sampled water from another location of the natural flow, this one downstream the mine, natural flow site 3. Finally, we collected water samples from the acid lagoons that belong to the mining flow site 1, mining flow site 2, and mining flow site 3. With an appropriate electronic device provided by the Losal Science Center, Mine of Science, we made measurements of temperature, pH, and electrical conductivity of each of the solutions collected. The results are as follows.
The results obtained for samples natural flow 1, natural flow 2, mining flow 1, 2, and 3 correspond to the expected values of temperature, pH, and electrical conductivity in each one of those water flows. However, the sample from the site downstream the mine, natural flow 3, showed lower pH and much higher electrical conductivity than would be expected. And this made us think that these results might possibly reflect the contamination of the natural flow by the mining flow downstream the mine, which would be a serious reason for concern if proven true. Therefore, we decided to ask ourselves, what's behind this local pollution? Does it really come out from the mine? To answer this question, we were challenged by our Ieso mentors to carry out a practical experiment at the chemical laboratory of the Losal Science Center.
Firstly, we collected several samples of rocks containing pyrite from the mining tailing heaps and reduced them to powder using hammers and mortars. Then, we added 15 grams of the powdered pyrite-rich samples to 2 of the 3 beakers containing 100 millimeters of distilled water each one, being the unaltered one the control test. Immediately after, with the help of the above described measuring device, their temperature, pH, and electric conductivity were recorded. Finally, to increase reliability, a copy of the experiment was performed, and both were left to rest. In the next day, the same measurements were taken from the stagnant samples and all the results were entered in a single table.
These results led us to conclude that the low pH values and the hyper concentrations of metal ions in the water of mining flow are directly caused by the reaction between water and the metalliferous tailings containing pyrite and other minerals. In theory, the pyrite in the tailings heaps oxidizes in contact with the air, generating sulfur trioxide, a compound that combined with water gives rise to sulfuric acid, following these equations. As the water becomes acidic, its dissolving power increases, integrating more heavy metals into the aqueous solution, and becoming a dangerous polluting agent. Hence, some measures urged to be taken to promote environmental rehabilitation and protect the existing biodiversity.
Regarding this, many people might think, so, if mines cause this much pollution, affecting all our systems, and still entail damage to the miner's health, why not just stop them? However, this apparent solution is completely unfeasible because mines are absolutely fundamental to society, since they are the source of a huge number of resources used on the production of most of our daily life objects.
Instead of ending mining, the solution is to invest in green mining, where the extraction process is done in a social and environmentally responsible manner and not just for profit. Thus, the life cycle of a mine should comprise the following steps: 1. Exploitation, 2. Evaluation, 3. Development, 4. Production, 5. Closure, and 6. Land reclamation. Basically, this sector should be grounded on the circular economy principles: reduce, reuse, recover, recycle. And the more developed countries, which are also the main consumers of resources, should assume the responsibility of exploiting those resources in a sustainable way, wherever they occur, including their own territory. The NIMBY policies are a kind of eco-hypocrisy.
For old mines exploited when there were no environmental concerns, which caused many ecological aggressions and life destruction on their surroundings, there are also measures that can be taken to mitigate the negative impacts and recover the area. When it is possible to carry out full environmental recovery of the impacted mining areas, the rehabilitation strategies generally consist of removing all polluting residues, for example HIPs, from the mining activity, preferably reusing them, treat all contaminated soils and water, and close all cuttings. Finally, renew the fauna and flora of the ecosystem with reforestation and creation of pastures for animals.
However, sometimes it is not possible or convenient to make a total recovery of the environment. In these cases, the areas that are irremediably polluted should be contained and isolated from the hydrological circuits to preserve the surroundings. This is normally done using impermeable barriers around the contaminated land. Fortunately, much of the modern mining is green mining, and many reclamation and remediation processes has also been carried out on degraded and contaminated ecosystems resulting from old mining operations exploited with no environmental concerns in the past.
In the case of Losal, when the mine was closed, no environmental recovery measures were immediately taken. Therefore, many environmental aggressions remained and required a significant rehabilitation plan. To mitigate this problem, Empresa de Desenvolvimento Mineiro, EDM, the public company responsible for the rehabilitation of degraded mining areas in Portugal, implemented the bioremediation project for the Losal mine. The first phase of treatment consisted of cleaning the soil by concentrating all the pyrite found in specific landfills next to the lagoons, which were sealed in order to avoid contact with the natural flow.
Then, a second phase took place in 2014 with the creation of a wetland system composed by a downhill sequence of 17 tanks, where limestone-driven pH correction and metal extraction by the roots of metal hyperaccumulated plants were inserted. Then, part of the mining flow, including water from one of the 3 contaminated lagoons, was erected into the wetland system for bioremediation. The above referred as bioremediation flow is, in fact, the flow of contaminated water under the treatment that crosses the sequential tanks by gravitational force. After passing through all the wetland system, the treated water flows into the Corona stream, supposedly clean and neutralized. In addition, most of the mine shafts and galleries were sealed and reforestation was carried out.
EDM's initial plan was to treat all the acidic and contaminated water. However, it would not be possible to fully eliminate these waters, since they keep being constantly contaminated by heavy metals that come from the tectonic faults that exist in the soil inside the lagoons. In face of this, EDM changed its initial plans, and decided to leave this lagoon and the adjacent one as they were, reinforcing only the containment dam to avoid contamination of the Corona stream.
It was also decided to leave the old mining infrastructure intact and to use it to create a science center called Mine of Science, which belongs to the Portuguese Ciência Viva network. The intention is to use this situation as an opportunity to create an educational tourism center devoted to science and technology, which may show the real and devastating consequences of a mining operation developed with no environmental concerns. Other initiatives includes a mining museum, a small hotel, and a restaurant.
So, this leads to another question. Does the bioremediation system really work? To answer this question, we carried out another practical experiment. First, water samples from several tanks of the bioremediation flow were collected and analyzed, as we had already done for the mining and natural flows. The results allowed us to conclude that, as we proceeded along the sequence of the first 4 water tanks, the pH was gradually increasing.
So apparently, the bioremediation system is actually working. To understand experimentally how it neutralizes the pH, we designed another experiment. We started by adding 30 grams of lime to one of the prepared pyrite solutions from both tests, stir well with a stick, and recorded the same variables. The next day, we repeated the measurements. The higher pH values of the lime tests prove the effectiveness of limestone against acidity. Basically, when lime is added to the solution, it reacts with water, creating calcium hydroxide, a strong base that neutralizes the sulfuric acid. The longer the reaction time, the more effective the reaction.
It is now time to return back to our previous question. If the bioremediation system is functional, how should we explain the high acidity and electric conductivity measured at the site NF3 of the natural flow downstream of the mine? Could there be a failure in the containment system of the mining flow?
Fortunately, there is an explanation for this situation. No, the containment system, like the bioremediation system, is working as expected. However, as we are in the summer season in Portugal, a very dry season in this part of the country, there is less water in the bioremediation flow. So the solutes are more concentrated, with the water being more acidic and having a higher concentration of metals than during the rest of the year. On the other hand, the segment of corona stream natural flow, where sample NF3 was collected, has an extremely low flow in the summer, as it corresponds to a meander zone, which allows for some acid water reflux from the wetland system, allowing the sample taken to reflect an abnormally low pH value. The best evidence for this is the fact that further downstream at the NF4 site, the measured pH of the water in the corona stream has returned to approximately neutral value, 6.82. That is, it has already been corrected.
After carrying out all this work and research, we came to the following conclusion. Mines are essential for the quality of life of human beings, as they are the source of mineral resources that enable the sustainable development of society.
Irresponsible mining can have serious consequences for environmental and social health, and can even lead to the destruction of entire ecosystems in such a way that an ordinary mine can affect both the atmosphere, in the way that when it's being exploited the equipment and transport necessary emit polluting gases, and the hydrosphere by acidifying the waters. Therefore, the biosphere is also affected due to the destruction of numerous habitats, the lack of organic matter available, and the massive extermination of different species.
However, if mineral exploitation is done in an ecologically responsible way, none of this will ever happen. The solution to having a good industry and a good environment is green mining.
Not only is Ieso an excellent example to see the negative impacts of a non-ecological mine, but also an excellent example for noting that it is in fact perfectly possible not to harm the environment with mining activity. It shows as well that there are creative ways to use mine rehabilitation projects to foster objectives as noble and useful, as social and economic recovery, educational purposes, science and outreach, and heritage defense.
In conclusion, if you kill the mines to save the environment, you kill us all. If you only build mines to develop the society and you totally ignore the environment, you kill us all too. On the other hand, if you do green mining in a sustainable way, we all survive. Thank you very much for your attention. We hope you have enjoyed our presentation. A friendly hug from the Portuguese national team.